Bismillahirrahmanirrahim. So we have a problem here. Let x and y be discrete random variables with the joint PMF, which is given below. P x comma y is equal to 0.01 for values of x from 1 to 3 to 10, and values of y from y is equal to 1 to 3 to 10, and this is 0 otherwise. So what is the PMF of v is equal to max of x comma y? So before we begin the solution to this problem, let us see the nature of the random variable v is equal to max x comma y, right? So max x comma y, it means that the maximum value of either of x or y. So if x is greater than y, then the maximum of these values is x, and if otherwise y is greater than x, then the maximum of these two values is y. So in other words, we can write it something like this: max x comma y is equal to x when x is greater than or equal to y. So when x is greater than y, then the maximum of these two values is x, and it is y when the y is greater than x, right? So this is how this random variable v, derived random variable v, which is a function of the other two random variables x and y, is defined. So before we begin to derive the PMF of v, it is better that we derive the CDF of random variable v, right? So basically, let's look at this scenario, that max x comma y is less than or equal to v, right? So it could be that x is greater than or equal to y, and then max xy is equal to x, or y is greater than x, and in that case y is y is the maximum value. So we can combine this with the two more scenarios. So we can say that if x is greater than or equal to y, and we are considering this max x comma y less than or equal to v, then so as x is greater than or equal to y, so max xy is x now. So it means that x is less than or equal to v. So if the maximum value is less than v, then the minimum value, the smaller value, will also be less than v. So we can say that, and also y is less than or equal to x, and it should be less than or equal to v also. So we have x is less than v and y also less than or equal to v. In other case, if y is greater than x and maximum of x comma y, the same scenario we are considering, right, is less than or equal to v, then so in this case the maximum value is y here. So maximum value is less than or equal to v, so we can say that y is less than or equal to v, and when the maximum value is less than v, the smaller value will also be less than or equal to v. So in that case x is also less than v and less than or equal less than y and less than or equal to v. So we see that in either case x is less than equal to v, right, and y is also less than or equal to v. So in other words, we can say that max x comma y less than or equal to v, this implies that x is less than or equal to v and y is less than or equal to v. So this will now facilitate us to derive a relationship for the CDF of random variable v in terms of the CDFs of random variable x and y. So CDF of v, fv of v is given by probability that v is less than or equal to v, right? So that is, so v is equal to max x comma y. So we write max x comma y here instead of v, and that is less than or equal to small v, right? So we have already concluded that max x comma y less than or equal to v, it implies this. So we can here write it something like this, that this is equal to probability that x is less than or equal to v and y is less than or equal to v, right? So now this is the if you see the joint CDF of random variables x and y, and if x and y are independent, if x and y are independent, actually this is the definition of independence, that if x and y are independent, then probability that x less than or equal to v, y x less than or equal to I would say x small x, y less than or equal to small y, then we can say that probability that x less than or equal to x and probability that y is less than or equal to y, right? So this is by the definition of independence of random variables. So we can write this relationship in a different way also. So probability that x is less than or equal to v multiplied by the probability that y is less than or equal to v. So this, if you see carefully, is the CDF of x evaluated at value v, and this is the CDF of random variable y evaluated at value v. So we can write it like this. This is fx. It will be v here, you know, it's evaluated at v here. If had it been x less than or equal to small x, we could have written x here, but this is evaluated at value v, right? So this is fy of y. So this is the in general relationship when we have to derive a random variable based upon this scenario. So the CDF of random variable v, which is max of x and y, is given by this relationship. But here we have been given the joint PMF instead of the CDF. So we can look at it at a different angle also. So this joint PMF here is plotted here also. So for example, for x is equal to 1 to 10 and for y is equal to 1 to 10, the value for each point is 0.01. So these are the 10 points in this row, these are the 10 points in this row. So 10 multiplied by 10, this is total of 100 values. So 100, 10 multiplied by 10, and the probability corresponding to each point is 0.01. So the total probability is 1. So this is a valid PMF function that we have been given, right? So for our specific problem, let us choose an arbitrary value of v, right? Let us say we can say that any value, let x is equal to v, some value. So x is equal to v, let's draw a line. X is equal to v is a line, you see, straight line along y-axis. So similarly, if we say that y is equal to v, so then this is a straight line like this, horizontal line along the y-axis. So if we are to consider for example the probability that v is less than or equal to v, then this is equal to the probability that x is less than or equal to v and y is less than or equal to v. See, we have derived this here, right? So this fv of v is basically probability that random variable v remains below this arbitrary value v here. So this relationship we have already derived here, right? So v less than or equal to v is equal to this probability now. So now this straight line, this represents x is equal to v. This straight line represents y is equal to v. So as x less than v is this region, right? Is this region, and y less than v is this region, right? And less than or equal to v also will include these lines also. So this is the region of interest here. This is the value of the probability that we want to calculate. So if you see, so if you want to calculate the probability in this region, you need to count the total number of points. So the length of the number of points in this row and the number of points in this column, they will be multiplied together with the value of the probability, like we did here. To calculate this entire probability of this entire region, we multiplied the number of points in a row with the total number of points in the column with the value of the probability of each point. So in a similar manner, the length of this row is 1 to v, right? So this is v in length, and the column is also v in length when you include the this value v, this column also. This is less than or equal to, right? Not less than alone. This is less than or equal. So v is also included here. So length of this row is v multiplied by the length of the column v multiplied by the value of the probability 0.01. So this comes out to be 0.01 v square, right? So in a similar manner, if we wanted to calculate v less than v only, less than, not less than or equal to, we removed the equal sign here. So in that case, the length of this row will be v minus 1. So this is v here, so this is v minus 1 here. So v minus 1 multiplied by v minus 1 here, and 0.01, the value of the probability. So this will be v less than v is equal to v minus 1 square multiplied by 0.01. So this is the probability when v is, capital V is less than small v, right? So we are interested to calculate the PMF, and which is equal to probability that v is, capital V is, takes on a small value v, right? And this in turn is equal to probability that v less than or equal to v minus probability that v less than v, right? So we have already calculated both these values. So v less than or equal to v is given by this 0.01 v square minus this value here 0.01 and v minus 1 square, right? So we already have these values now. So PVFV is given by 0.01 into v square and minus 0.01 and 0.01 could be taken common, but let's do it in the next step. 0.01 v square minus 2v and plus 1, right? So PVFV is equal to 0.01, let's take it common. So we are left with v square minus v square plus 2v and minus 1. So this cancels out and we're left with 0.01 into 2v minus 1. So this is the probability model of the derived random variable v. So you also see that the derived random variable v takes on values from 1 to 10 like x and y. So because this is the maximum of x and y, it cannot be lower than 1 and it cannot be greater than 10 because it is chosen from x and y. So if x and y take values from 1 to 10, so v also takes on values from 1 to 10. So the complete PMF can be written like this: 0.01 into 2v minus 1 for v is equal to 1, 2 to 10, and this is 0 otherwise. So this completes the solution to this problem.